To reach the Moon's south pole, we require machines that defy the limits of current aerospace engineering. The heart of this mission is the Space Launch System, SLS, the most powerful rocket ever developed by NASA, standing at over 320 feet tall, taller than the Statue of Liberty. The SLS is a marvel of brute force and precision. It generates 8 million pounds of thrust during liftoff, a power necessary to break free from Earth's gravity and push the Orion spacecraft into the deep vacuum of space. The development of the SLS involved thousands of engineers, suppliers, and scientists, all working in synchrony to ensure that every single bolt, weld, and line of code is flawless. This rocket is not just a carrier, it is the launchpad for the future of humanity. Complementing the power of the SLS is the Orion spacecraft, the crew sanctuary during the long transit to the Moon and back. Orion is designed to withstand the hellish conditions of deep space re-entry, where temperatures reach over 5,000 degrees Fahrenheit as it hits the Earth's atmosphere at nearly 25,000 miles per hour. Its heat shield, a pinnacle of material science, is designed to ablate, slowly burning away to carry heat away from the crew module, keeping the astronauts safe inside. Unlike the capsules of the Apollo era, Orion is built with modern, integrated technology that allows for increased autonomy, ensuring that the crew can handle complex systems even when communications with Mission Control in Houston are delayed. However, the most groundbreaking aspect of the Artemis 3 mission is the inclusion of the SpaceX Starship as the Human Landing System, HLS. This partnership represents a shift in space exploration, combining NASA's decades of deep space experience with the rapid innovation cycle of the private sector. The Starship is, in its own right, a revolutionary machine. Designed to be fully reusable, it is massive, with a pressurized volume that far exceeds any previous lunar lander. Its sheer size means it can carry more equipment, more science experiments, and more life support consumables to the lunar surface than ever before. The integration of these three massive systems, the SLS for initial propulsion, the Orion for crew transit, and the Starship for the final descent to the lunar surface, is an engineering challenge of unprecedented scale. Each interface must be perfectly synchronized. The complexity of the docking maneuvers, where the Orion and the Starship will meet in lunar orbit, requires sub-millimeter precision. These maneuvers will be practiced, repracticed, and refined in high-fidelity simulations for thousands of hours before the mission even leaves the launch pad. Every contingency, from a system failure in the lander to an emergency abort maneuver during the descent, is accounted for in the mission's flight software. Furthermore, the technology needed for the actual stay on the Moon is equally critical. The lunar surface is a hostile environment. It is subject to extreme temperature fluctuations, ranging from 250 degrees Fahrenheit in the sun to minus 200 degrees in the shade. The lunar regolith, or dust, is sharp, jagged, and abrasive, capable of damaging spacesuits and mechanical seals. Developing materials that can withstand this environment, while keeping the astronauts comfortable and productive, is a massive undertaking. The next generation of extravehicular activity, EVA, suits, the Exploration Extravehicular Mobility Unit, XEMU, is designed with modularity in mind. These suits allow for greater range of motion, allowing astronauts to bend, twist, and reach in ways that Apollo astronauts could only dream of. The communication infrastructure supporting this mission is also a technological feat, with the distance between Earth and the Moon being roughly 240,000 miles. There is a delay in communication. The mission relies on the Deep Space Network, a global array of giant radio antennas, to maintain a constant data link with the crew. This link carries not only voice communications but also high-definition video feeds, health metrics, and the torrent of scientific data that the mission will generate. Ensuring this link remains unbroken is vital to mission success. Behind every piece of this hardware lies a philosophy of reliability and redundancy. In space, there is no room for error. Every system has backups, and every backup has a failsafe. This redundant architecture is what allows us to look at the vast, empty expanse of space and see, not a barrier, but a frontier. It is through the relentless pursuit of engineering perfection that we have reached this moment. As we prepare for the integration and testing phases of the hardware, the world watches, waiting to see these machines roar to life, not as separate components, but as a cohesive force of human ambition. This journey demands perfection, and it is a challenge our finest minds are ready to meet.